Okay, this is section 3.2, and it's on the Rolle's theorem and the mean value theorem. And in a nutshell, Rolle's theorem says that if you've got two x's and you've got a graph, and the y values for those two x's are the same, Rolle's value guarantees there's at least one value, or you have a minimum or a maximum, which is a critical point. Okay. Now, the reason that is because if you just, I'm going to kind of talk over here to the side for a minute while I, just since I've got this picture up here already. The reason that is let's say you've got a graph. Maybe I'll draw in red over here. Okay, so let's say that I've got a graph, and let me pick a red color again. Let's say you've got something, let's say there's a parabola, and if I look, we draw a line right here, there's 2 points on this graph that have a y value that are the same. Well, if they're the same, 3 things can happen. Either it went down like I drew this one, and there's a minimum here. I'll draw on the same graph. Those 2 points, it could have gone up like this, and there's a maximum somewhere because it has to go up. Or if it doesn't go up, the only other option is that it's like a horizontal line. And let me draw that in purple. The other option is that it's a horizontal line. Well, on a horizontal line, really what it says, what the Rolle's theorem says is that if you remember from 3.1, our critical values, our maximums and minimums, happened when our slope was 0. And our slope was 0 is when we had a horizontal line as a tangent. So here's a horizontal line as a tangent there. Up at the top, there's a horizontal line as a tangent in the second case that I drew in green. And if you have a horizontal line, well, the slope, if you remember, the derivative is the slope. Well, what is the slope of a horizontal line? It's 0 at every point on that line. So there are an infinite amount of places where there is a slope of 0 there. So Rolle's value theorem says that you're just guaranteed that you've got some place where the slope is 0. And where the slope is 0 is usually where there are critical points. So most of the time, this is not such an important theorem by itself so much as it works in tandem with section 3.1 to guarantee that we've got something. But there's two caveats there. The function has to be continuous, and it has to be differentiable. So if we look at number 1 here that I've got, I tried to zoom in here, but if you look in your book, they've got a graph here of number 1, and I'll use some green to write since I've got writing all over on this. If we're to explain why Rolle's theorem doesn't apply to this function, even though there exists, like if we look here at the first function, number 1, you got 0, 0, and 2, 0. The y values are equal. So you would think that Rolle's theorem would guarantee that there is a place where the derivative is 0, the slope is 0, so we'd have a maximum or minimum. I can't even use that here because look at this point right here. Do you remember that this is not differentiable at this point? And the reason is the limit from the left is not equal to the limit from the right. So anytime we got these sharp curves on things, the limits from the left and the right are not the same, so we can't say those functions are differentiable. It wouldn't apply here because that point's not differentiable. Another thing is look at number 2. Rolle's theorem would not apply here because you've got these asymptotes right here, and so the function is not continuous, is it? So if it's not continuous or it's not differentiable, Rolle's theorem doesn't apply. So these, right off the bat, they're showing you 2 places where Rolle's theorem does not apply. If you look at number 3, this is an absolute value function of some sort. Rolle's theorem is not going to apply because that's going to be just like number 1. You can put it in your calculator and see what happens. Well, there's another problem too. Look at in that fraction on the bottom, you've got an x. What if I plugged in 0? 0 is in this negative 1 to 1 domain set here. If I plugged in 0, I would get an undefined fraction, so the function would not be continuous at x equals 0. So honestly, probably for number 3, the better reason to give for why it's not differentiable is that it's not even defined at x equals 0, and 0 is between negative 1 and 1. Remember, this is our domain they're giving us here. Number 4, our domain here is negative 1, 1. If you were to put number 4 in your calculator, you'd see, and I forget exactly what it looks like. I remember we did this one in class, but I'm kind of making this video after class for those of you who were not here. This function either went up like this and came down. It could have been like this, I don't remember, but either way it did something like this, and you kind of had to maybe blow up your graph to really see it, a good copy of it, but this would not be differentiable. Either of these cases wouldn't be differentiable because you'd have these sharp points on your graph, so your function's not differentiable there because the limit from the left and the limit from the right are not the same thing. That's something we talked about in the very first chapter, so you might need to go back there if you're a little confused about the limit thing. In both the Rolle's theorem and mean value theorem things, if you notice, there's two things in common that have to happen. The function has to be continuous on the interval they're looking at, and it has to be differentiable. Now, the mean value theorem says that if you pick 2 points on the graph, like an interval on your graph, then there exists a number where you're going to hit your average rate of change. Your slope is your average rate of change. And when we did distance equal rate times time, for instance, we always found our average over a certain time period. Calculus deals with the instantaneous rate of change. So what this theorem is saying, it's not really all that helpful except in proofs. This theorem is saying that if we take an interval and we look at it, we look at the derivatives across that interval, then there's going to be some point on that interval that we're going to hit the average rate of change. Because remember, the average is just the lows and the highs, all the things just averaged together. You kind of get the middle. So wherever your 2 points are, it's basically saying that somewhere in the middle there is the average, okay? So I thought I would work a couple of problems that might have to do with the mean value theorem, like number 39. When I'm going to give you quizzes and stuff over this stuff, this is more likely what you're going to see on it is stuff like this. So I want to make sure we talked about just some simple things here. Okay, so let's say I've got the equation f of x is x squared. That's a parabola. It's just the parent function of a quadratic equation, actually. And we're looking on the interval -2 to 1, and it says determine whether the mean value theorem can be applied to f on the closed figure. If it can be applied, find all the values of c in the open interval such that f prime of c, the derivative, at a certain point is f of b minus f of a over b minus a. Okay, so what's going on here is that what I want to do is first of all think about the function. And I can use my calculator if I'm not familiar with the function, but this is a pretty straightforward one. It looks like this, except I've got it more lopsided. It's a nice U-centered, symmetric about the y-axis there. We're going to look from -2 to 1, so maybe somewhere in here is where we're going to look. The mean value theorem, if this function is continuous and if it's differentiable, it says that the average rate of change occurs somewhere in that interval. I can use the mean value theorem here because it is continuous and differentiable. So yes, the mean value theorem applies. So how would I use the mean value theorem to find the average? Well, if I want to find the average rate of change, that's the slope, the average slope. That means that's the average derivative. See how you can kind of think your way through this. Rate of change is slope, and slope is the derivative. If I want to find out where that occurs, what I can do is say, okay, I can use this little formula. This is just a slope formula. So if I want to do this, all I got to do is go back to my function, and this is the function y equal x squared, and they give me two x's, the endpoints of the closed interval, -2. If I square -2, I get 4. The other x they give me is 1. If I square 1, I get 1. Remember, this is my A. We're going to call this my A, and this my B here. And the x are your A's and B's. Remember, the y is just your f of x, right? So f of A is 4, okay? And f of b is just 1, okay? You're just saying what's it's the difference of the y's over the difference of the x's, just like when you were in Algebra 1 and you were learning all this. So f of b is 1, and f of a is 4, and then b was 1. Remember, this is a, this is b here. A was 2, so 1 minus -2, so that's a -3 over 3, that's a -1. Oh, my average rate of change is -1. So where is, okay, so my average rate of change is 1. So how am I going to find where that occurs on the graph? Well, This is telling me the derivative of some point is equal to 1. Go back up here. What's your function? It's f of x equal x squared. Take the derivative. Well, the derivative is just 2x. Okay, well, if that's the derivative, we're saying the derivative is equal to 1 at some point. So all I got to do is say 2x is equal to 1, and then divide both sides by 2. Oh, the average rate of change happens at 1/2, at x is 1/2. That's my C value they talk about in the mean value theorem. So this is where my average rate of change occurs. So if you notice what we did is we just said, oh, the slope is just, the derivative is just the slope. Let me plug all my stuff in and find out what the average slope is, the average rate of change is. It's 1. Well, where is that? Where does the slope of 1 occur? Well, it's where when I take the derivative of the function, it's equal to 1. So you go take the derivative of your function, you get 2x, you set it equal to your slope that you found over here, and you find the x value that gives you that slope. That's all you're doing here. It sounds very complicated. It can be kind of hard to wrap your brain about, but it's not really hard if you kind of think about what's going on here.